Move more into the frame. You don't want to be on camera. Stand over there.
She had that need for that. And I said, I don't. I'll tell her. Tom, could you trust me with one of the girls and I gotta go there. There's probably even it. Yeah. And then we still work on it. And we try to pay over it. She's like, I'll show her. I'll have to probably by not. And then Bill is like, how do you drop policy? It's like, where are you giving us those two? We have this. No, what she did, I'm pretty sure what she did is that I'm gonna walk out. I want you all, no, she said, I'm gonna walk out.
I've watched her cut.
That was in the middle of
My fault.
Marcus is a talented kid, but I don't think he's learned calculus backwards.
No, it was Andrew.
Guys, have a good day. See you all shortly.
He's probably asking really nicely in that one. I just like kill it in the I mean, this other kids feel so stupid, they would know what's going on and be like, you don't know what a trig is? Exactly. Literally.
How do you do that?
Oh, I try not to do it. I got this biology the first year. Alright, you know, I'm like, I'm thinking back when I was about freshman year. Michigan Gilly would be like, alright, test coming up. I would be like, cool. And then ignore that, like, I didn't do anything for it. And I'd be like, what is Excel? I'd be like, I don't know. Oh, no. Are we supposed to turn sideways? I'm sure my family's sideways. What's this? So I want to turn sideways, we're going.
No.
Damn it. God, come on.
I don't really want to do it.
Look at that first team James shirt. I just have one Tony shirt that has no color.
Is that what you do?
Let's see if anyone responded yet. Today is 7 question. If you could visit one place in the world, where would you be?
That didn't take a ball to hit Japan.
Huh?
That boy Jacob trying to go to Japan.
Well, what's the attendance question?
You go anywhere in the world where you want to go.
It's, okay, I remember there were two of them, no, one was like quantum,
That'd be
like
great.
quantum, or quantized. Like,
Yeah, get fresh.
oh, okay, one of them was
Lucy.
quantized, and one of them.
Try to post up in front of the
Both.
Yo.
Post up in front of the camera. With Team James.
No, I'm not trying to post up. Did I give your homework back?
Yeah.
Okay, cool.
He's gonna watch it back.
Shout
it out.
I-Z.
What's that?
That was Mitchell.
What's up?
Team James, bro.
There you go.
Mother, you first, watch me, this is work on it. Yeah.
Words and questions.
They won't let you look at it, they take this part and show you. And then repeat it. Yeah, so, let me cut it off a little bit. Good luck with that. We're not going to do it. She's like that. You know what's fun now, number guys. If you want to affiliate with the game, team games, please come to the office. I got mine to work. What? I got mine to work. They work where? Good. Yeah, when I go through my car, I'm a little weird, but I mean, it's still working. As long as it launches. It should. But it never launches. I just want to find the equation of the tangent line.
You're facing that wall, one way or another. Want to turn your desk, that's fine. Got a plethora of homework to show. Let's go ahead, let's get that out. Let's get started with going through that. We gotta talk linearization today, also known as tangent line approximations. For this class, I'm looking for 3, 4, 3, 5, 3, 6, and 3, 7. 3, 4, 3, 5, 3, 6, and 3, 7. I'm going to start with you looking.
It's still not going to be seen, but put down on the task, but give him your test script. Set. So we try, that's what I want to see. With, equal, definitely percent good. Oh, okay. Yeah, same thing. I will repeat, I should see that all the way over. This is not something we'll try to see. Okay. Distance formula. That's distance formula. What?
see that work all the way out. Yeah. So here, this is good for this one right here. And we'll do the distribution. These tests will go, these tests all the way out. Yep. So it should take one full page to do each one of those problems. Nope. Distance one, says smallest distance. Ain't no typo there. No typo there. Distance form. Distance form.
That's the only test to do though. I wish.
We did this here, so that each time we do the graded test, first and second group. We will work with the exact same. Yeah, and I know that you want to, and I know that we probably can't, but work is required.
Sometimes you gotta get done.
Well, you have to run that on YouTube, when this was up with super sick, with the boost voice. Well, I wasn't in school that Tuesday. She is, but I tell you what, man, she had me scared. I've never seen her that sick before. I mean, she was throwing up every hour. And just, I mean, from 10:30 probably through 5:30 Tuesday morning. Just throwing up every hour. She didn't have COVID or anything. We went and got her tested just to be safe, but she would probably would have liked to have lost taste. Doing all that, but yeah. It was rough, but I thought it was just funny, you know. Oh, it was too well, and then all of a sudden, getting sick, I'm gonna play parts. It's definitely parts. Yeah. That's an all over. Great. I do it. And it wasn't clearly.
I use calendar, just not giving runners much of this one, you know, because every time it's like, I'm getting it done. So it's a week thing, it's like, my fingers are still.
I've seen that maybe a little bit more.
That's the second picture. Yeah, I was getting on the line together and I saw somebody drop his profile and I was like,
It's not that good, but you know.
Yeah,
We're recording.
This one is basically. This one goes a little So the amount of work that I expect. Number two, there is no typo. Well, I need to get more graph on our little equation was, and I told you use distance formula.
Well, there's no.
Equation is square root x. Find the point on the graph y equal x squared, that is the smallest distance. So you have a graph, x squared.
There's no y equals x squared.
Well, why is there not? Well, why is it not? Okay, so obviously we can talk about that one. We can talk about that one. It's very similar to the one I did on our live stream, which is something that we need to talk about with you all. You all. Because it ain't a problem with your counterparts on B-Days. You need to show up to live stream. It's 10 o'clock in the morning. It ain't that early. It's not like I'm asking you to wake up at 8:30. I'm asking you to be up out of bed by 10 o'clock and log on to YouTube. That's your attendance. You guys are fortunate and lucky that it continues to log and I continue to keep it up there so that you can go back and rewatch it. But you need to show up, you need to be there, and you need to be more engaged and asking questions and being involved. It is that simple. I most certainly am not doing it for my health. And while it is a little bit less work for me than pre-recording the videos, it isn't enough to warrant the amount of work that it takes to make it work all the time. It's a trade-off, and I'm doing it for you all. Certain lessons are way better done live, even if it's through the webcam, than it is you doing a pre-recorded video. How many of you guys watched actually logged in Friday? Okay? How many of you didn't, but had to go back and rewatch the video? How much easier would it have been if you were here asking questions? Now understand that that's a full live recording. So if I go back to pre-recorded videos, there's nobody asking questions. There is no call or response. It's not like you're sitting there in class. For some of you, it'll probably want to make a big difference. For others, it will. You need to show up. It's just that simple. Part of your attendance. Okay. Let's see how much time we got to kill with this today. What homework questions do we want to do? From which section, Michaela? 3.7, number 4. Luke? 5 from the same section, sure? 2? Since 2 wasn't all the way there. Parker?
15 from 3.6.
15 on 3.6. I might not do all parts of 15. I might give us a general outline for parts of 15. Okay? Just because if I try to do all of 15, I'm going to fill this whole board once or twice over. Okay. I do want to start with 15 because I think 15 is a good idea of what I expect to see when I start grading your quizzes in a little while. What I expect to see when I start grading the quizzes in a little bit. So let's grab our book here. Go to section 3.6 and let's look at problem number 15. So, for number 15, what do we have going on here? We have the equation y equal to x squared minus 6x plus 12 all over x minus 4. Correct? I am on the right page, 215, right? Okay. I don't need the book because I got to basically do everything. You got to do everything from top to bottom with this problem. I'm going to start with the easiest things before I get into derivative tests. I'm going to start with end behaviors, asymptotes, things like that. So my degree on the top is higher than my degree on the bottom. So I know that I'm going to have a horizontal, I will not have any horizontal asymptotes. Won't have any. Now technically, that means we'll have a slanted asymptote. That the asymptote that we would approach is actually going to be a line, like y equal 2x plus 5, y equal 3x minus 4. That's actually going to be our asymptote. That's something that you guys aren't 100% familiar with because you guys are always used to asymptotes going right through the axes, either perfectly vertical or perfectly horizontal. But you can have slanted asymptotes, and that is actually the situation that you would be looking at for this type of problem here. The way to find that asymptote is to actually do this division with synthetic division and find that equation. That is what you actually have to do to find that asymptote. So, we need our first derivative, second derivative, we need all that junk. We are going to have, of course, a vertical asymptote here at x equal positive 4. So, let's do our first derivative. For that, we're going to have to set up a quotient rule, f over g, g squared, g f derivative minus f g derivative. G derivative easy, 1, f derivative not too bad, 2x minus 6. Okay, so as we set this up here, we're going to have x minus 4 over 2x minus 6 minus x squared minus 6x plus 12. all over x minus 4 quantity squared. We'll FOIL this out here. We're going to get 2x squared. That should be minus, it's going to make 8x, 14x, and plus 24. Minus x squared plus 6x and minus 12 when we distribute our negative through. All over x minus 4 quantity squared. Let's simplify this out. To get our first derivative, that's going to be x squared minus 8x and plus 12. All over x minus 4 quantity squared. Are we all okay so far with what I've done? Yes, no, maybe? Okay. I prefer to go ahead and do both derivatives now, and then I'll go back and run each test individually. So let's pick up with our second derivative right below here. We're going to have to set up another quotient rule. So f over g here. So this is going to be my f and g. G here is going to be 2x minus 4. That's our g derivative. And then the derivative of what's inside, of course, is 1. F's derivative should be a little easy. It's going to be 2x minus 8. So when we set this up, g f derivative minus f g derivative all over g squared. Here's what we're going to be looking at. We got x minus 4 quantity squared times 2x minus 8 minus 2x minus 4. And we got our x squared minus 8x plus 12 all over x minus 4 to the 4th power now. Here. We all okay so far? I'm going to get an x minus 4 group from everything here, so that's going to give us 1 there. It's going to knock this down to 3 and kill that one off completely. I'll send my negative 2 through. I'll FOIL. What are we looking at here? This is going to be, let's FOIL this. That's going to be 2x squared minus 8x minus another 8x. Yeah, minus 8x and then minus another 8x. So that's going to be minus 16x and plus 32. When we send that negative 2 through, we're going to have minus 2x squared plus 16x and minus 24 all over x minus 4 to the 3rd. Let's get our x squareds out of here. Let's get our 16x's out of here. And that leaves us with 12 over x minus 3 quantity cubed. Are we okay with my derivatives? I think I did them right. Pretty sure. Mr. Kaufman is human and prone to error. So no lie when I said that I was going to fill this board twice over, because I'm not even halfway done with this problem. Now I actually have to run my test, get my zeros. Okay. 8. What did I put? I put 12. Yeah, it is 8. Thank you, Michaela. Not that it's going to make a big difference here, but that's still, we should get it right. Okay. Let's go ahead. Let's do my derivative test here for this one. So we have first derivative does not exist at, of course, x equals 4. Of course, we can set that up. X minus 4 equals 0. X equals 4. That's no surprise that is our vertical asymptote here. What else we're going to have is, of course, where it's equal to 0, which is where we have 0 x squared minus 8x plus 12. Will that factor? In fact, it does. X minus 2, x minus 6. That gives us critical values at 2 and at positive 6. So we must test those. 2, 4, and 6. While 4 itself won't be a maximum or a minimum, it could be a point where we change from increasing or decreasing. So it still needs to go on the number line here. Okay, let's see. If I put in 0, what's going to happen? 0, 0, positive, it's going to be plus. Okay, if I put in 1, or not 1, we need to put in 3, what's going to happen? Well, that would be 3 squared minus 8 times 3 plus 12. 3 minus 4 squared, that's just going to be 1. That's going to be 9 minus 24 plus 12. That's negative. Okay? Let's go with 5. 5, that's going to be 1. 5 squared, 8 times 5, so that's 25 minus 40 plus 12. That is still negative. And then, of course, on the other side of 6, we put in 7. That's going to be 3 squared. It's going to be 49. It's going to be minus 56. Plus 12, that is going to be positive. So we got plus to minus. That's looking like a max here for 2. Looking like a max at 2. And a minus to positive, so we're looking at a min there for 6. We need to fill those in, so back over here at 2 squared minus 6 times 2 plus 12, all over 2 minus 4. 4 minus 12 plus 12, all over negative 2. The 12s cancel. 4 over negative 2 is negative 2. Okay, and then we need to put in our 6. So 6 squared minus 6 times 6 plus 12, all over 6 minus 4. The 6's cancel. I'm left with 12 over 2, which is 6. So that's the results of my first derivative test, is my max min. And we can do our increasing intervals. We're increasing between negative infinite and 2, as well as between 6 and positive infinite. We are decreasing between 2 through 6. Well, actually, it should be 2 through 4, and then 4 through 6. Because we can't actually have 4, so we've got to adjust it. Are we okay with what I've done so far? Oh, my goodness. Okay, on to the second derivative test. This can't equal 0, but it can, of course, be, what did I get? 3 from that's 4. So we do have, of course, f double prime does not exist at x equals 4, because, of course, that's our vertical asymptote. Outside of that, we need to figure out concavity. So 4, let's put in 3. If I put in 3, I'm going to get negative 1, and that'll be 8. So negative here. If I put in anything higher than that, it's going to be positive. So we are concave down between negative infinite and 4, and we are concave up between 4 through infinite. Okay. This is the abbreviated version of the work that we should see, because I did not do the work actually for these two asymptotes, which should be somewhere over here. What's more is I'm not drawing the graph because I'm out of space and we have a whole lesson to do, and I got 3 other problems to get done. Questions here? So if this is my minimum level of work for what I'm doing up here on the board, when I look at your quiz and I have all these exact same questions, if not more so, I expect more work. Caleb? Okay. It really does suck that I was not here to teach that one on the live stream. That is absolutely a lesson I wanted to do via live stream and not have to do with the pre-recorded video. But it is what it is at this point. Okay. Number 2 is very similar to a question that I did in class. We got y equal to x squared. We're going to set up our distance formula here. And we have a 0.06. We're going to put that point in for x and y. X minus 0 quantity squared plus y minus 6 quantity squared. This one is going to be best done like we did in class, where I'm going to swap out rather than when I look at this here, y equal to x squared, I can actually substitute that directly in. So rather than getting rid of y, it's actually easier to get rid of x this time. So this is going to give me a square root of y squared. Nope, not y squared. Just y, actually, plus y minus 6 quantity squared. So this gives us y plus y squared minus 12y plus 36 gives us y squared minus 11y plus 36. Are we all okay with what I've done so far? Yes, no, maybe? Or
Can't you just plug the x squared into y?
I could, if I want to make everything x to the fourth. If I put that in, if I put x squared in for y and put it in right here, first off, it would go in right here, so that would become x to the fourth, which is going to be y squared. So that would be this squared. So that becomes x to the fourth minus 11x squared plus 36. So I mean, you could do that. Don't get me wrong. I think it's just easier to stick with y here than it is with x. And here's your equation, the one that you all were wondering where it is. Here it is. Do we need to keep going, or are we good? What would we do next? What's the next thing? Derivative test, right? Run the first derivative, we find the max min. In this case, we're looking for min, right? And it should be a min. I mean, this is standard quadratic. It opens upwards. That's a minimum value, right? Okay. That's number 2. What else do we want to look at? 4 and 5. Let me put up my answer key for 4. I feel like that might help you all just to see how I drew the picture for number 4 real quick. And then I'll work it back out a little bit more. This one might have to be the last one we do. We might have to skip over the next one just because we're running out of time. I got to get our lesson in today. P7, optimization, homework. So this is how I recommend setting up number 4, is like this, where I have my y as my 3 vertical lines and my x as my horizontal line. So it looks something like this here as I'm drawing it out. So x will run from here to here, and each of these distances are y. Okay? So if I have 102 meters of fencing, of course, that means that all my x's and y's total will make that 102. So that gives me 2 x's plus 3 y's make my 102 fence. Does that make sense? And that's what I have right next to it. You can see that. And then, of course, the next thing here is we want what's the maximum area. So we have area is equal to x, y. So this is what we want to maximize here. So you can really get rid of either one x or y here. It's really your choice. Pick your poison. But once you get this set up, it's up to you. If you want to get rid of x, you can. If you want to get rid of y, you can. What did I do in the answer here? I got rid of x, so I kept y's. But you could do differently if you so choose. Questions here? Okay, so I'm going to go ahead and move on. If we have time, we'll try to come back to 3-7, number 5. Let's start with our linearization. Let's start with our tangent line approximations. Start with tangent line approximations here. So, are we ready to begin? Okay. let's move on to slide 2. Let's talk about linearization here. As we move on here, for those of you in class, I do have printed off copies of our notes here today. And for them at home on Canvas, they have, well, they're just going to have to look off the PDF. So I think that's what happened, by the way, with why that y equal x squared didn't pop up for number 2, is for some reason Canvas doesn't like Microsoft Word, and it won't upload equations that I put in Microsoft Word. So I'll have to make a mental note, because that's also what happened with our one test, if you remember. A bunch of the equations didn't show up. So I need to start exporting things as PDFs. So I'll try to remember that for us. So let's look at slide 2 here, so that way we can start with some questions. So we're going to jump into this with a hypothetical. So let's say that some mysterious radiation happens, solar flare, and it fries all the technology on the planet. Fries all the technology on the planet. We're back to the post-apocalyptic medieval ages. No calculators. Best of luck with you and your abacus to do your math from now on. Now you all laugh, but legitimately, this is one of the actual doomsday scenarios that governments around the world actually do have plans for, because solar flares are real. And it's very possible that one of them could actually wipe out most of the technology on the planet. They emit a giant electromagnetic pulse burst and could fry all computers. Not all of them. I mean, some of them are EMF proof, but still. I'm pretty sure you guys don't have those lying around your house. So what do? Obviously, we don't want the world to crumble. We don't want to descend into post-apocalyptic madness, though that probably would help Mr. Hoffman with his student loan debts and his mortgage payments. But nonetheless, most people probably want it. Not everybody's ready for Thunderdome law like I am. So, how do we keep things together? So we need to be able to do math again, old school. Way, way, way old school. Older school than Mr. Kaufman even remembers. So, to fix this, we're going to go ahead and start with doing some basics like square roots. How would we do a square root that doesn't work nice and neatly, like the square root of 5? So, obviously, we'll start with the equation y equal to the square root of x, right? So, what we'll do is we'll get a close approximation. We don't need it to be perfect. We just need to be roughly where we need to be. So let's start with that x equal 4. We know the square root of 4. We know that comfortably is 2, yes? 4 is relatively close to 5. So what I propose is that we find the tangent line for y equal square root x at the point x equal 4. What does that entail doing? How did I get that equation in blue? What have I done? How do we find the tangent line? Dom? We'll do the derivative, because we don't need calculator to do that, right? So let's go ahead and let's run the derivative here for our y equal square root x. Of course, Dom, we're going to rewrite that as 1/2, correct, x? And we've done this derivative like a bunch of times. We've dealt with these roots. This shouldn't be anything crazy for us. Can you give me what that derivative will be? 1 over 2 root x. Now we're looking at specifically at the point 4, right? So 4 goes in. What are we looking at here? 1 over 4. So that's how I got the slope for that line, yes? Some of you don't do this. I'm going to encourage you to start. You're going to want to start keeping things in point slope form. That's not in point slope form, but you're going to want to start doing this. So, this would be our point slope form here. All I did was send the 2 to the other side. I didn't even bother reducing it down. So this is our equation of our tangent line. So the reason why we're after this is because if you look at the function, at the graph, right? At 4, of course, we're tangent. We are equal to that point. We've touched at that, right? But this line, while it's not touching at 5, it is really close to where the graph should be at 5. That's the whole gimmick behind doing a derivative in the first place, is we're doing a limit as we get closer and closer and closer and closer, right? So as we get closer, let's just use that value at 5 as our approximate value.
Does that make sense? Because we're getting closer as we close in on it, right? Even though this isn't exactly what it's going to be relatively close to where it should be, because that's the whole gimmick behind a derivative, is that as it closes in, the line gets closer to where it should be, right? So, using this, what we would do is that since this gets so close and the curve itself almost follows this tangent line, not precisely, but almost, let's use 5 in for this tangent line. Let's put our value in that we're after, the value we're going to approximate, in for this tangent line. So, y minus 2 equal to 1/4, 5 minus 4. This is going to give us 1/4, and of course 1. This is going to give us 2 and 1/4, or 2.25. Correct? Okay. So that's what our... Yeah, go ahead. So that's what our line kicks out. That's what our approximation line kicks out, is 2.25. Okay? So the actual square root of 5 is 2.236, right? I have it up there. That's pretty close, ain't it? I mean, we're talking tenths, hundredths. For most things in reality, hundredths is pretty good. Unless we're dealing with something with hyper precision, where hyper accuracy is needed, this is going to be pretty close. This is going to be pretty close for what we need it to be. If we were doing, let's say, banking, would you care about the difference between 1 cent? No, probably not. I don't think Jeff Bezos cares about 1 cent. Bill Gates probably doesn't. Questions here? So this is the general idea as we skip through our slides here. So we are on to, so we went through slide 3, and now we're finishing up slide 4. And this is what we've done. And this is the math that we're talking about, and this is our logic behind it. So this is what we call linear approximation, or linearization, if you will, where we use the tangent line to make a rough prediction or rough estimate of a value. Questions here? This is actually what businesses use calculus for most of the time. When you talk about cost and profit models, they are not nice linear graphs. They curve up and down as, of course, supply and demand and cost of materials and cost of labor fluctuate. You have your up seasons, your down seasons. So you have a very curved graph when it comes to your cost and profits. So what advanced software does, a software typically called Salesforce, does is run these advanced derivatives so that way you can make, okay, roughly, approximately how much cost am I looking at going into this month? How much profit should I be looking at for this quarter? That's how calculus is used in the real world. That's what these problems would actually end up being as application problems. So let's try to keep things a little bit less heavy right now, though. Let's go on to slide 5. So in general, what I want you to know, in general, in slide 5, is that for any function, I can use my tangent line, my first derivative tangent line, at a specific point, to be a good approximate, provided that it is a small distance from the point in question. Provided that when I find the tangent line, I'm doing so close to the point in question. So I was able to do this because 4 is very close to 5, right? Now, very close depends on the situation, and that's where we get into the application parts, right? Like, for this, for money, probably not a big deal. For hundredths in medicine, it is a very big deal. There are medications where a couple milligram difference can go from being totally fine to being whacked out to a few more milligrams and you're just dead. Right? So like it's not foolproof. It's case by case. Let's go into slide 6. So slide 6 is the same thing I got in your notes right there. This is our step-by-step rules. These are my guidelines for doing linearization. And we don't have to write them down. They're right up there at the top of the note sheet for you all. 1, 2, 3, 4, 5, 6. Right? So first thing we'll do, find the derivative. Take the function that we're after, find the derivative. Just like we did here, what Don did in black. Then we use our derivative to find the slope at a point that is close to, but not the one actually in question. So if I'm looking at, let's say, square root of 15.5, I might use 16, because 16 is a perfect square. If I'm looking at, doing, let's say, a cubic root, because we're dealing with cubes or roots here. I might, if I'm looking for 7, I might use 8, because it's a perfect cube. Right? So, you got to keep things in mind. We'll get our tangent line equation at that point that we're using as our base. Then we'll plug in the actual point we're trying to estimate into that tangent line. That's what we did in blue, was find the tangent line, and then in purple, we plugged in the actual point that we're going to estimate on. Does this make sense? So this is one of those skills that we're going to talk about today where most of the time, in reality, you have to do this. In fantasy math class land, where everything works nice and neat and you have Desmos and everything else, typically this doesn't seem like it has a lot of practical usage, a lot of practical application. It's typically only once you get out into the real world that this becomes something that you need. Questions here? Concerns here? Okay, a couple of things to tell you. This does relate back to our second derivative, which is why we're talking about this right now. Is if my second derivative, if my function is concave up, that means my tangent line will be skirting underneath the function. If it's concave up, I'll be skirting underneath the function. So anything that is concave up, this tangent line will be under what it should be. It'll be an underestimation. If the function is concave down, the tangent line will skirt over top of the function and therefore be an overestimation. Once again, in math fantasy lands, big deal. Who cares? In reality, this would be pertinent information. If I'm overestimating my profits, that's a problem. We don't want to overestimate how much money we're coming in with, right? So if I know that this estimation is going to be high, I'm going to reduce it down for my client when I tell them that. If we're dealing with medications, depending on what it is, we might want an under or we might want a little over, depending on what it is and who it is and a bajillion other factors, right? Once again, this is a very unique case-by-case kind of situational problem. But because it relates back to the second derivative test with concavity, and we have first derivatives going on here, I think you see why I kept it in this particular section. I also don't think that you wanted to do Newton's method, which is 3.8. It's not super fun. I thought that this would be a little bit easier since I just drilled you guys with 3.7 and 3.6. And our last quiz didn't go so great. I'm curious to see how this quiz goes. So, now that we're finished up on slide 7, that should actually finish up our notes there, right? That's all the more notes I have for the day. Let's jump into a few example problems, okay? Let's jump into a few example problems. Are we all set here? We're all on the same page here. All right then. Let's go on to, what is it, slide 7? We want to go into slide 8. So slide 8. So we're going to stick with the square root function. Something easy to do because I just did it. I'm going to go ahead and determine the approximate value near 16. We're going to approximate 15.5. So I did this very similar up here. I want you to go ahead and try example 1 without me. I think you should be able to do it. Go ahead and give it a try. Follow the step directions up at the top of the notes, step 1, 2, 3, and 4. I'm going to filter around, answer some questions. Those of us at home, let's make sure that we're following along. Give this one a try here. Example 1, if you have any issues, type them up in chat. That way, if we have problems, I can address them. Whether it's I'm having trouble getting the tangent line, or have trouble getting this, or I don't know what to do, whatever those questions might be. So slope of the tangent line, right up the tangent line. X is fine, slope is fine. Slope is fine. The y value is not right. Square root 16 is not good. I'd like you to tell me, once you finish, will this be an overestimation or an underestimation? Should this be an overestimation or an underestimation?
Yeah.
Let's check on the chat here. Let's see what's going on. Oh. All right. Let's take a look. So here's where I began. In my little blue box, found the derivative. Of course, we already have it up here because Dom's excellent work right here. Now, this is where a bunch of us started making mistakes. Is right after we got this, is what we need to do with it. So first thing we got to do is not put in 4 because I'm not using 4 as my counterpoint here. I'm using 16. This is going to make this 1/8 for my slope. Here's where a number of us also made a secondary mistake, is these numbers are not the same anymore. This is going to be 16. A lot of people have changed that one. That's fine, but you forgot to change this one. So at least 2 or 3 of you put down 2 here. Square root of 16 is not 2. Square root of 16 is 4. So that's what I have here in my paint box, is getting this equation started. From here, it's just evaluating down. Everything that needs to go in. So we got 1/8, 15.5. That doesn't look like 15.5 at all. Try that again. Minus 16. minus 4. A bunch of you sent that 4 over immediately, and that's fine. That's what I did on the last one too, so it's okay. Solve it down. I got y to be 3.9375, which I think comes out as like 63 over 16 or something like that, right? It's just short of being a full set of 4. Are we all okay here? We're all comfortable here. Okay, is this an overestimation or underestimation? Doug? It is an overestimation. Why is it an overestimation? Because we are concave down. We want to pick this up and show that this be 1 over 2 x to the negative 1/2. For us to quickly show this here, we just got to prove that this function is concave down. So the double prime here, the second derivative, that would be negative 1/4 and x to the negative 3/2, or negative 1 over 4 cube root of x squared. And then you can just throw in 16, but it doesn't matter because that's going to spit out, of course, this is always going to be a positive number going into this cubic root, which means the cubic root is only going to spit out positive numbers, which means my numerator is always positive, my numerator is always negative, which is always negative. This is a concave down function everywhere. It has no points of inflection. Questions? So, heads up about a possible problem. I could ask you to do this linear approximation and then prove to me that this is an overestimation, or prove to me this is underestimation, which means go run your second derivative test, right? Now you can see maybe a little bit more clearly why I kept this rather than doing Newton's method. Because Newton's method is a whole different set of testing rather than first and second. Questions here? Concerns here? See if we have any questions on chat. Doesn't seem like it. Let's move on to the next example then. Let's move on to our next example here. Move on to slide 9. Move on to slide 9. A few of you started this already, so go ahead and get working on it here. Example number 2. How would you approach a question like this? Example number 2, slide number 9. I'm trying to keep track of what you got. What X's do you have? What Y's do you have? Do you have any slopes? That's right. We'll work between point A and point Z. How about you show me the equation at some point? And go back and put it at some point. So there's no this. Mhm. Let's see. What are those? What are they? So let's do that as an X, 1.5. Okay, what's our answer? Let's start with that. What is it? 9. Very good. I gave you everything you needed. You don't need the equation because I gave it all to you. Gave you the point 0.25, gave you the slope 10. Plug it all in, solve it down. Point is 9. Questions? Easy problem to do for slide 9, right? Easy problem. Okay? That's it. I'm not going to torture us here today with anything else. I've done enough of that as of late, I think. Not going to push the envelope. You got these 5 problems for homework. A couple of you already almost done. Or not 5 problems. What is it? 3, right? No, there should be 5. There should be 2 on the back, isn't there? Oh, there's a bunch on the back. Okay. I was about to say, it should be at least 5. I remember adding them. As we said earlier, Mr. Kaufman prone to mistakes. It is only the second time I'm teaching this class, so I think I'm doing a lot better job this time around than last. So, finish out these problems here. That's your homework assignment. What else I'm going to do before I'm going to let the live stream go is going to tell you that because last week didn't go as according to plan, and because our last quiz was a little bit rougher, and I am concerned about when I start grading this one, I'm going to give you a little bit more time to do your test, a little bit more focus for that. So tomorrow we are just going to work on our study guide. And we'll take any questions that we have to go over. I might do an extended warm-up here for us tomorrow just to kind of be ready for our live stream to watch. But then we're going to work on our study guide. On Wednesday, you just have your test. I'm not doing anything else for you all on Wednesday. It's just your test. I have to be here to give the ACT. There will be no office hours on Wednesday. So that's the trade-off is not that many of you were coming to ask questions in the first place, but I won't be able to answer them. So your test will be due on Friday. You have all day Wednesday to work on it. Thursday and Friday this week, we are going to move on to Unit 4, though. So use this time to get yourself caught up on the different things you need to get caught up on. I have not yet decided what I'm going to do with our IXL stuff yet. I'm still deciding on what I want to do with it. I'm going to wait and see how our quiz and our tests go before I decide how I'm going to use that. Any questions about it? Okay then. Well, get working on your homework. And those who saw our live stream, unless we have any questions, you guys can go ahead and bug out. And I will see you all on Thursday or tomorrow for our warm-up problems at least.